Hey guys, we are going to spend a little bit of time. I'm just going to go back over the electron configuration notes so you have a resource to go back to if you're struggling with these. So we briefly went over kind of how we got to the quantum mechanical model and this idea that we don't know exactly where an electron is, but we know where it probably is. And we have this idea that they exist in these orbitals, which are those regions of space where the electron has that highest probability of being found. So we want to be able to describe the locations of these orbitals by the distance from the nucleus, by the shape of the orbital, by their orientation in space. So we're going to start kind of breaking down those different pieces. So the first thing is that we started with and that we've already talked about are those principal energy levels, which we can also call shells. Those help tell us the distance from the nucleus. Okay, and that's going to be that letter N, where we talk about like the first shell and the second shell and the third shell and so on. Those are giving us the information of just how large the orbital is and how far away it can exist from the nucleus. And we talked about kind of how that increases, and we'll go over that in a second. Now, principal energy levels are pretty general. They're just giving us that distance part. So those shells are made up of our sublevels or our subshells. Okay, and this has to do with the different shapes there. So this is going to do with our shapes. And this is going to have to do with some letters that you'll see. And you saw this in the gizmo. So we have the S, sublevel, P, D, and F. So those are all, and there are more outside of that, but those are the four that we discuss here. Now those sublevels are then comprised of our orbitals. Okay, the different orientations of them, the different spin of the electrons within them. And we'll eventually get to that more specifically when we do our orbital diagrams in the next lesson. So let's just primarily go over our sublevels and our shells and just go over some important information for each one. So with this, the principal energy levels, which we've talked about a little bit when we did atomic spectra. Remember, this has to do with that size, the distance from the nucleus. So the greater distance from the nucleus, the greater the energy. So that first energy level is the closest. Those electrons have the lowest energy. And then as you move further away and you get to the farthest energy level, those electrons have to have the highest energy. Okay, they're able to exist that far away from the nucleus because they have enough energy to overcome some of that attraction. Okay, and our Bohr diagram gives us that general description. So for like oxygen over here, which is 2-6, we have 2 electrons in the first shell and 6 in the second shell. That's just giving us that general principal energy level. Now it is helpful to know the maximum amount that each level can hold, and this will make sense of where these numbers come from when we go to do sublevels. So they all fit this 2n² model. Even the principal energy levels 5, 6, 7 that are theoretical also fit that. So the first energy level can only hold 2 electrons. It's the closest, it's really small. It can only hold those 2 electrons there. The second energy level is going to be able to hold 8. The third energy level is going to be able to hold 18, and the fourth can hold up to 32. So those are good numbers to know because it will kind of help you check to make sure you're going to be filling the electron configurations correctly. All right, so those are very general principal energy levels. Those, again, are made up of sublevels or subshells. So our subshells are our S, P, D, and F. So which ones are in which energy level has to do with our value for N here. So for the first energy level, it only has one sublevel, which is the S sublevel. 2 is going to have 2 sublevels within it, and it has an S and a P. So like this would be our 1s, and then we would have 2s and 2p. And then our third has 3 energy levels, which is S, P, D. And then our fourth has 4 energy levels, which would be an S, P, D, and F. Okay. All right. So the type of sublevel is related to the shape, which I had mentioned. So S takes on like a spherical shape. P takes on these different figure 8s that move along each of the axes. D has a 4-leaf clover shape, and we'll kind of go over that tomorrow. But it has to do with the shape. And each type of sublevel can only hold a maximum number of electrons within it. So like S, which only is that spherical shape, can only hold 2 electrons. Okay, has 1 orbital within it. The P sublevel in entirely, so there's 3 different orbitals in P. So as a group, as a sublevel together, they can hold up to 6. D sublevel can hold up to 10, and F can hold 14. So when you take a look at this, it should hopefully make sense. Like if I look at the second energy level, okay, it can hold 8 electrons because it has S and P. If I look at the third energy level, it can hold S, P, and D, so that's where that 18 electrons come from. Just so you can see the relationship between all these different numbers that we're going over. And again, we've taken our principal energy levels, okay, first, second, third. Then we have our sublevels, S, P, D, and F. And then those sublevels are going to get broken up into orbitals within those sublevels, which we'll deal with tomorrow when we do orbital diagrams. All right, so let's work on actually how to write these electron configurations. So there's a couple of ways that we can go about writing these. The first big thing, though, is that all of these are going to follow the Aufbau principle, which is the buildup principle. This is that electrons are added to orbitals with the lowest energy first. And you would think that in general we would do, okay, 1s, 2s, 2p, 3s, 3p, 3d, but there's some exceptions, and eventually we'll go over this unit of why we have these exceptions. For right now, you just have to be aware of them. One big exception is that 3d always gets filled after 4s. So ways to catch this exception, and it has to do with the shape of an s orbital versus d, and we'll get into that when we get into the periodic table, is how we're going to catch these discrepancies between them. So there's 2 ways. One is drawing and being able to write this diagram, which if you look for the pattern, you have 1s, 2s, 2p, 3s, 3p, 3D, and you can see how S, P, and D line up. This tells you the order to fill. So like if we were looking at this diagram, and I'm just doing it for not any particular element, we would have 1s that would get filled first. S can always hold up to 2. Then I would get to the bottom of the next arrow. This would be 2s, and then 2. And then I go to the bottom of the next, we would have 2p. P can hold up to 6. Then we have 3s, which can hold up to 2. And then we have 3p, hold up to 6. And this is where the discrepancy, because you would think 3d would come next, but right now 4s, because it actually has lower energy, is going to come next, which then this would be 4s, holds up to 2. We would go down to the bottom of the next arrow. I'm just going to have to put this below. This would be 3d up to 10. Then we would have 4p, which p can hold up to 6. And after 4p, you would have 5s. Okay, so that's just one way like to fill it up. So like if I have an element or an atom that has, say, 18 electrons, okay, I would have, here's my 10 and here's my 8. So this would be the configuration for that. So this is one way you can do it. The other way is to use the periodic table. So a lot of students will start with this until they start to get comfortable writing these, and then they'll start to rely on the periodic table. Another one, start with this. So here is that diagram that I had you fill in. We did it together in class. So you can remember that here we have our S block elements, including helium. We have our P block, D block, and then our F block. And just remember, I'm going to use this as part of my example when we go through them again, is that everything kind of has a purpose of where it is. So the row on here that it's in for S and P corresponds with the energy level that gets filled last. D, remember, is just 1 less. F block ends up being 2 less. It also shows you, like in the P block, if I had chlorine here, I would know that I would be filling 1s, 2s, 2p, 3s, and then I would have 3p. I would count 1, 2, 3, 4, 5, finish at 3p5. So at some point, I really do want you to spend some time making sure you can understand this, and I'll do, again, some of these with the practice, because this can be really helpful for just doing them very quickly. I do find that this diagram is more helpful when you get into some of the really big atoms that have a lot of electrons, where you're starting to mess with like the F block within there. Okay, so let's actually try these out, because I think that's going to help. And here's just another diagram to help you as you're kind of sorting through these configurations. And again, this is showing you essentially like the order that we're filling them. All right, so we're first going to do just the full electron configurations for these 3. So we have chlorine on here, and chlorine, and we have vanadium, and antimony is SB. Okay. So for this full electron configuration, chlorine has 17 electrons. Okay, so I'm going to use my periodic table here. So the first thing it's going to fill is the 2 electrons in 1s. So I'm going to have 1s and it can hold 2. Then I go start the next row. I'm going to fill 2s because I have 2 electrons available. Then I'm going to fill 2p all the way to 2p6. So I'm up to 10. I need 7 more to fill in. So I'm going to do 3s2. Okay. And then now I'm into my p block. So since I already have 12, I just have 5 more electrons left. I can't completely fill it, so I'm going to count over 1, 2, 3, 4, 5. So this would be 3p5. All right, so let's pick up. I just had to go grab a reference table so that way I could show you guys a couple things. So we just blasted this chlorine one. So I'm going to jump to vanadium. Okay, so with vanadium, which has 23 electrons, vanadium being 23 is right here. So we can see that if this is in the 4th row, I should be at the end filling 4s2 and then going over and doing my 3d. So this would end up in my 3d block, and it's the 3rd one over. So if we check that, and just using this to initially kind of help with this, I'm going to fill in 1s first with its 2 electrons. Then I'm going to fill in 2s. Then I'm going to fill in 2p6. Then we have 3s2. Then I'm going to fill in 3p6. And then I still have, so that's my 10, my 18 electrons. So then 4s2 right here gives me up to 20. And then it makes sense that I have 3 left. So that's going to be going into 3d. So that is 3d3. Okay, so you can see how this periodic table and knowing the structure of it and how it aligns to the electron configurations can help filling these a little bit easier. It's also helpful when it comes to writing the condensed electron configuration, or sometimes called like the noble gas abbreviation. Okay, because really as chemists, we get mostly concerned with those outermost electrons. So we have a way of condensing this down using the noble gases to do so. So for chlorine, the process of this is you would look at, and this is in my 3rd row, I'm going to look at the row above it and the noble gas that comes at the end. So that would be neon. So I'm going to start with the brackets for neon. Now on my little periodic table here, neon is where 2p6 is. So this symbol covers everything up through 2p6, and then I would fill after that. So then I would say, okay, here's my 3s2 and then my 3p5. So 3s2, 3p5. Okay, I can also do this for vanadium. So vanadium was in that 4th row. So I'm going to go up to the 3rd, go all the way over until I get to argon. So I'm going to first fill in the brackets for argon. Okay, argon exists in the 3rd row down where 3p6 is. So when I go to do vanadium, I'm going to use that symbol to cover everything up till that point, and I'm going to fill in from there. So that's where I would have my 5s2 and then my 3d3. Okay, so hopefully you can see how those two tie together. So let's do antimony. What you can do is see if you can pause the video and try the full and condensed electron configurations, and then always check it. So for antimony, which is Sb, it has 51 electrons. I should be able to look at this periodic table, and I can see that it is in the 5th row in the p block, 3rd one in. So I should end up with 5p3, okay, when I get to the end of the electron configuration. So let me first just initially with you fill in the first part that you kind of have been seeing quite a bit. So we know that we're going to start off with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We haven't gotten this far yet, so let me go this part with you. I'm going to fill in all of 3d10. Then I have 4p6. Okay, then I'm going to get to the next row here, which is my 5s. So 5s2. Okay, and then I'm going to get to 4d10. Okay, and if I count, that should give me, I have my 10, 20, oops, let me check that, 10, 20, 30. I feel like I'm, oh yeah, 30, 40, I'm at 48. So I have 3 more electrons, which makes sense because I have my 3 to fill into 5p. So here's 5p3 over on the side there. Okay. All right, so that's a lot to write. So this is definitely one that we would want to use the noble gas configuration if we could. So with SB is in the 5th row, I'm looking at krypton that's in the 4th row above it. So here I'm going to have krypton. Okay, krypton is where that 4p6 is. So I'm going to fill in everything after that, which is my 5s, 4d, and 5p. So I have 5s2, 4d10, and then 5p3. So you can see that that's a lot more condensed, shorter to write, but you definitely want to understand how that noble gas is involved with that. All right, last little bit here, we're almost done. This is just our exceptions on the periodic table that you have to be aware of. We will get into kind of the evidence that supports this and why this occurs, but for right now, I just want you to be aware, so when you're writing these, you're going to start writing them correctly. So the first two are chromium and molybdenum. So if I write out chromium's electron configuration, the abbreviated one, you would have argon, and then would be, you would think, 4s2, 3d4. But the evidence doesn't actually support this. What they find is that one electron from 4s actually exists in 3d. So instead, we are always going to write chromium as 4s1, 3d5. Okay. They find that it exists at a lower energy state with this. And again, the evidence is going to support that this is how these electrons actually get filled. Molybdenum, which is right below, is super similar to this. Molybdenum has krypton as the noble gas before it, and you have your 5s and 4d in this case. And instead of 2 and 4, it's actually going to, again, one of those electrons is going to move up so that this is 5s1 and then 4d5. Okay, you kind of see that comparison there of that half-filled D sublevel. And also visually, this will make sense to you when we go to do orbital diagrams in the next lesson. The other three exceptions all also kind of go together. We have copper, silver, and gold. These are going to completely fill their D sublevel instead of completely filling their S sublevel. So for copper, copper is like right in the same row as chromium. So it's going to use argon as its noble gas part of its configuration. And then for this one, normally we would have 4s2, and then it would be 3d9. Okay, it exists in this spot right here. But what they find is that doesn't actually exist as 2. One electron actually does exist in 3d. And the reason for that, again, has to do with the fact that that will completely fill the D sublevel, and the evidence and just the energy of the atom supports this. So this will be your 4s1, 3d10. Silver is just, again, very similar. You would have krypton here, and then this would be 5s1, and then instead of this being 2 and having 4d9, that one electron moves up so that this is 4d10. All right, so again, you should be able to see the pattern here of S and D sublevels. The last part here, just with silver, I want to go over, because if you go to write this out, you'll have xenon, and then you would think that this is 4s2. You would actually then fill 4f14 next, and then you're going to have your 4d9. Okay, but ignoring 4f, leave that alone. This is just, again, still involving S and D. This will exist as 6s1, so that 5d exists as 5d10. Okay, and again, you should be able to see the pattern there with S and D. So again, make sure you're aware of these exceptions. We will get into later this unit why these exist, but for right now, just make sure you are filling them correctly when you get to do them.